What if I told you Pluto, the tiny frozen rock at the edge of our solar system, is actually alive? Not with life, but with a secret that's been hiding for decades. A secret so strange, so unbelievable, that it's rewriting everything we thought we knew about planets. Scientists expected a dead, lifeless rock. Instead, NASA's New Horizons discovered mountains taller than the Rockies, flowing nitrogen glaciers, and a glowing blue haze in its sky. And the temperatures? Far colder than physics said was possible. But here's the crazy part. Pluto's sky is literally cooling itself, thanks to microscopic particles working like a giant invisible air conditioner. And the James Webb Space Telescope just confirmed it. In this video, we're diving into Pluto's mind-blowing secrets, how its haze controls its climate, how it paints its moon Charon red, and why this tiny dwarf planet could change everything we know about planets, moons, and even life in the universe. You're not going to believe what Pluto is doing. Stick around. You'll want to see the part where James Webb captures Pluto's secret for the very first time. For decades, Pluto was nothing more than a distant dot, a frozen, forgotten rock drifting at the edge of our solar system. Small, cold, and lifeless. That was the story we were all told, until one spacecraft changed everything. In July 2015, NASA's New Horizons probe raced past Pluto after traveling more than 9 years and over 3 billion miles through space. No one knew what it would find. Some scientists expected a dead, cratered world. Others hoped for a few surprises. But when the first images began to stream back to Earth, the world stopped. Pluto wasn't a dead rock. It was alive, a frozen world bursting with motion, color, and mystery. We saw towering mountains made of solid water ice, standing taller than the Rockies. We saw vast glacial plains of nitrogen flowing slowly like rivers across the surface. And we saw something that stunned every planetary scientist on Earth, a soft, blue atmospheric haze glowing around the planet. A haze. How could a world so small, with gravity barely enough to hold onto a thin veil of gas, have an atmosphere so beautiful and dynamic? It was something no one predicted. As the images sharpened, scientists realized the haze wasn't just a faint blur. It was made up of more than 20 distinct layers, stretching over 150 kilometers high into space. Each layer caught sunlight differently, creating a surreal, layered glow that made Pluto look almost Earth-like, yet entirely alien. But the real shock came when New Horizons sent back the temperature data. Pluto's upper atmosphere wasn't behaving at all like it should. Every model predicted temperatures around 100 Kelvin, still freezing, but expected. Instead, it measured only 65 to 70 Kelvin. That's about 203 degrees Celsius, far colder than anything scientists could explain. Something was cooling Pluto's air more efficiently than physics allowed. Something strange was happening above that icy surface. Something invisible, silent, but powerful. And so, after that flyby, Pluto went from a blurry mystery to the most confusing world in the solar system. Why was it so cold? Why was its atmosphere layered like Earth's? And what was that ghostly blue haze made of? NASA's New Horizons had answered a few questions, but it had opened 1,000 more. And for the next few years, scientists all over the world began searching for one answer. What was stealing the heat from Pluto's sky? That mystery would remain unsolved for nearly a decade, until the James Webb Space Telescope finally looked at Pluto and discovered something no one had ever seen before. After New Horizons passed Pluto in 2015, scientists were left speechless. The spacecraft had revealed a world wrapped in a delicate haze, shimmering, layered, and breathtakingly beautiful. But when the temperature readings came in, those same scientists felt something deeper than awe. They felt confusion. Pluto's atmosphere wasn't just cold, it was far colder than it should ever be. Every model said its upper air should hover around 100 Kelvin, just as gases like nitrogen and methane absorb sunlight and trap a bit of heat. But reality told a different story. New Horizons measured only 65 to 70 Kelvin. That's nearly 40 degrees colder than science could explain. Something high above that icy world was siphoning away heat faster than any known process could account for. And no one knew what it was. At first, astronomers suspected the obvious culprits. Could carbon monoxide be cooling the air by radiating heat into space? Could nitrogen, Pluto's main atmospheric gas, be acting differently under those extreme conditions? Or could solar particles from the solar wind somehow strip away energy from the upper layers? But one by one, those ideas fell apart. The numbers didn't add up. The cooling was too strong, too efficient, and too widespread. That's when planetary scientists began to look closer at something most had ignored: the haze itself. At first, it was thought to be just a byproduct of methane breaking down under sunlight, a dusty, passive layer of fine particles. But what if it wasn't passive at all? What if the haze was the key? High above Pluto, sunlight strikes methane molecules with enough energy to rip them apart, forming complex chains of carbon and hydrogen. Molecules like acetylene, ethylene, and heavier organics. These molecules then stick together, building microscopic aerosol particles, tiny grains of carbon-rich material called tholins. They float and drift through the air, scattering blue light from the sun, painting Pluto's atmosphere with its ethereal glow. To most scientists, those tholins were just a pretty side effect. But a few began to wonder, could these tiny particles be doing something powerful? Could they be radiating heat away into space more effectively than gases ever could? That idea sounded wild, even impossible, but the numbers whispered otherwise. If those particles were constantly forming, constantly glowing in the infrared, they might act like a massive radiative cooling system, a natural thermostat that bleeds heat from the sky into the cold vacuum beyond. In 2017, a planetary scientist named Shi Jiang from UC Santa Cruz proposed a daring theory. He suggested that Pluto's mysterious chill wasn't caused by its gases at all, but by its haze particles themselves. He believed they were actively cooling the atmosphere by emitting energy in the mid-infrared spectrum, far beyond what any gas could manage. If true, it would mean Pluto wasn't just unique, it would be rewriting the rules of planetary climate science. But there was one problem. No telescope on Earth could see those faint infrared signatures. Pluto was simply too small, too far, and its light too weak. So the mystery lingered. For years, scientists had the theory, but no proof. They needed something powerful enough to see the invisible, to detect the faint glow of those cooling particles drifting above Pluto's icy surface. And that's when humanity built the one machine, capable of doing exactly that: the James Webb Space Telescope. When New Horizons sent back those haunting images of Pluto's atmosphere, one detail stood out more than anything else: that mysterious blue haze. It wrapped around the dwarf planet like a ghostly halo, glowing softly against the blackness of space. It was beautiful, but it was also completely unexpected. How could a world so small, so distant, and so cold have something that looked almost like Earth's sky? The answer, as it turned out, would reveal one of the strangest chemical processes in the solar system. High above Pluto's surface, far above its icy plains and mountains, the sun's ultraviolet radiation beats down relentlessly. Even though Pluto is nearly 40 times farther from the sun than Earth, those UV rays still have enough energy to reach it, faint but powerful. When they strike the upper layers of Pluto's atmosphere, they encounter methane gas, one of the key ingredients floating up from the surface. And that's where the magic begins. The UV light tears methane molecules apart, ripping hydrogen and carbon atoms from each other. What's left behind are reactive fragments, unstable, desperate to bond again. These fragments begin to collide, combining into more complex molecules: ethylene, acetylene, and eventually even heavier hydrocarbons. And as these compounds grow, they start to clump together, molecule by molecule, into tiny, solid particles, so small that a single one is thousands of times thinner than a human hair. These are tholins, some of the most fascinating substances in planetary science. They're complex organic solids, rich in carbon and nitrogen, and they can form naturally anywhere there's sunlight and simple gases like methane and nitrogen. You'll find them on Titan, Triton, comets, and even in the outer edges of interstellar clouds. On Pluto, these tholins drift slowly downward, suspended in the thin atmosphere. They scatter sunlight in the blue part of the spectrum. That's why Pluto's haze glows with that soft, sapphire light. It's not oxygen or nitrogen like our sky. It's organic dust, floating in the air of a frozen world. As they fall, these particles settle onto Pluto's surface, coating it with a thin reddish-brown film, the same tint seen in New Horizons color maps. That reddish tone is Pluto's signature, the mark of ancient sunlight, chemistry, and time. In a way, every grain of that dust is a cosmic memory, a chemical fingerprint of the sun's light interacting with Pluto's alien air. But here's where things get truly strange. These tholins don't just make Pluto beautiful, they may also control its climate. Some scientists believe that as these particles absorb sunlight, they re-emit it as infrared radiation, cooling the surrounding gas. If that's true, it means Pluto's atmosphere is literally cooled by its own haze, a planet whose sky acts as a giant natural air conditioner. This idea, once just a hypothesis, would soon be tested by a telescope powerful enough to see the invisible, to detect the faint heat glow of those haze particles drifting through the void. A telescope unlike any ever built before, the James Webb Space Telescope. By 2017, Pluto had become one of the greatest mysteries in planetary science. New Horizons had given us stunning images and priceless data, yet the numbers still didn't make sense. Pluto's atmosphere was far too cold. Every model, every simulation, every known law of atmospheric physics failed to explain it. But then, a bold new idea emerged. At the University of California, Santa Cruz, planetary scientist Dr. Shi Zhang began to suspect something radical, something no one else had considered seriously before. What if Pluto's haze wasn't just a passive veil of particles? What if it was alive in a way, actively shaping the planet's climate? Zhang and his team started to run the numbers. They studied the behavior of tholins, those strange organic grains born from sunlight and methane in Pluto's upper atmosphere. They already knew that these particles absorbed ultraviolet light and scattered visible light. That's why Pluto glows blue at the edge of space. But Zhang wondered, what happens next? After absorbing that energy, how do these particles release it back into the universe? When they simulated Pluto's atmosphere, they discovered something astonishing. These tholin particles weren't just reflecting sunlight. They were radiating heat away in the mid-infrared spectrum, a range of wavelengths invisible to the human eye, but crucial for cooling. In essence, Pluto's haze wasn't a blanket trapping warmth. It was a radiator, bleeding heat into the frozen darkness of space. Zhang called this idea the haze cooling hypothesis. It proposed that Pluto's atmosphere stays so cold not because of gases like methane or carbon monoxide, but because of the haze particles themselves. Each tiny speck of organic dust, floating miles above the surface, acts like a microscopic heat sink, constantly emitting faint infrared light that carries Pluto's warmth away. If true, this meant that Pluto had a completely different climate mechanism from any world we'd ever studied. A mechanism where solid particles, not gases, controlled the temperature of the air. That was revolutionary, because no planet, no moon, no atmosphere in the solar system behaved like that. But there was a problem. Zhang's model was based on calculation, brilliant ones but still theoretical. To prove it, scientists would need to see those mid-infrared emissions for themselves. And that was impossible. No telescope on Earth, not even the mighty ALMA array or the Hubble Space Telescope, had the precision to detect Pluto's faint infrared glow. The signals were simply too weak, too distant, and tangled with the light of its moon, Charon. For years, the haze cooling theory sat on paper, bold, elegant, but untested. Then, everything changed, because humanity was about to launch a telescope powerful enough to see the invisible. a telescope that could pierce through cosmic dust, detect the faintest heat signatures, and separate Pluto's light from Charon's for the first time. That telescope was the James Webb Space Telescope. And what it was about to find would finally prove Jung's theory and rewrite the rules of planetary climate forever. For years after Jung proposed his daring theory, Pluto's greatest secret remained just out of reach. The math made sense, the chemistry made sense, but science doesn't move on belief. It moves on proof, and proof, in this case, was almost impossible. Pluto lies more than 5 billion kilometers from Earth, a tiny world smaller than our moon, half hidden in the shadows of the Kuiper Belt. It reflects barely any sunlight, and whatever faint warmth it gives off is colder than the coldest vacuum chamber ever built by humans. Trying to detect its mid-infrared emissions from Earth was like trying to see the glow of a candle on a mountain from across the ocean. Every telescope that tried failed. The Hubble Space Telescope could capture Pluto's beautiful surface, but not its heat. The Spitzer Space Telescope, designed for infrared light, simply couldn't distinguish Pluto's faint signal from background noise. And there was another obstacle: Charon. Pluto's largest moon isn't just a companion, it's almost a twin. The two worlds are locked in a gravitational dance, always showing the same face to each other. To our telescopes back home, they appear almost as one, their light blended together, their thermal emissions intertwined like threads of the same fabric. Separating Pluto's heat from Charon's was like trying to hear a single whisper in a storm. So for nearly a decade, Jung's idea sat in limbo, admired, debated, but untested. The Haze cooling theory was elegant, but it lacked the one thing that could make it real: observation. What scientists needed was an eye powerful enough to see the invisible, to detect the faint infrared radiation that Pluto's haze might be releasing into the darkness. They needed a telescope that could look farther, sharper, and deeper than anything humanity had ever built. And in December 2021, that telescope finally took flight. A golden mirror unfolded in the silence of space, its panels glinting in sunlight like the wings of a cosmic butterfly. It was called the James Webb Space Telescope, humanity's most ambitious observatory, capable of capturing the faintest warmth from the edge of the universe itself. For Pluto, this was the moment everything changed, because Webb could do something no other telescope could. It could separate Pluto's light from Charon's, isolating their individual infrared fingerprints with absolute precision. At last, the impossible was possible. For the first time, scientists could listen directly to Pluto's whisper, the faint hum of its atmosphere, the glow of its haze, the thermal breath of a frozen world billions of kilometers away. What they would find next would prove that Jung was right and reveal a brand new kind of climate, unlike anything ever seen in our solar system. When the James Webb Space Telescope unfolded in 2021, humanity held its breath. It wasn't just another telescope, it was a time machine, a golden eye pointed toward the dawn of creation itself. But somewhere beyond the dazzling galaxies and newborn stars, a small icy world waited: Pluto. And though it seemed insignificant compared to the cosmic wonders Webb was built to study, it had a secret no one else could uncover. For years, astronomers had been blind to Pluto's true nature. Every instrument before Webb was too weak, too noisy, or too blurry to see its faint thermal glow. But this time, things were different. Webb was designed to look where no human eyes could ever see, in the deep infrared, the language of cold worlds and hidden heat. At the heart of this mission was an instrument called MIRI, the mid-infrared instrument. It wasn't just sensitive, it was revolutionary. MIRI could detect temperatures as low as 6 Kelvin, colder than deep space itself. It could spot faint infrared signatures coming from dust, ice, and molecules trillions of times dimmer than starlight. In short, it was the perfect ear to hear Pluto's whisper. So, when Webb's golden mirrors locked onto Pluto for the first time, astronomers around the world went silent. Data streamed down from a million miles away, not in photographs, but in spectra, those delicate fingerprints of light that reveal the chemistry and heat of a world. And there it was. For the first time in human history, Pluto's own infrared voice was heard, separate from its moon Charon, clean and distinct. The data wasn't blurry, it wasn't noisy. It was beautifully clear. Miri saw exactly what no one else could, a faint but undeniable mid-infrared signal coming from Pluto's upper atmosphere. It was the kind of radiation that could only be produced by tiny haze particles emitting heat, just as Xizang had predicted years before. To the scientists watching, it was as if Pluto itself had spoken after years of silence. A frozen world, 5 billion kilometers away, was actively managing its own climate, radiating its excess warmth through a haze of organic dust. The discovery sent a shockwave through the planetary science community. For decades, astronomers believed only gases like carbon dioxide or methane could control a planet's temperature. But now, a haze, something made of microscopic particles, was doing the job. This wasn't just about Pluto anymore. If haze could cool an atmosphere here, what about other worlds? What about Titan, Triton, or even exoplanets cloaked in smog hundreds of light-years away? The James Webb Telescope had done it. It had not only proven Xizang right, but opened a new chapter in planetary climate science. And the best part? This was only the beginning, because as the data kept pouring in, Pluto's secrets went even deeper, beyond haze, beyond cooling, into something that could change how we understand the chemistry of life itself. It happened in May 2023, a moment that would quietly rewrite our understanding of one of the most mysterious worlds in the solar system after decades of blurry data, overlapping light, and unanswered questions. The James Webb Space Telescope finally did what no other eye could do. For the first time in human history, it separated the light of Pluto from that of its moon, Charon. To most people, that might sound like a small technical detail, but to the scientists who had spent their lives chasing Pluto's secrets, it was everything. You see, for nearly 50 years, every telescope, even Hubble, saw Pluto and Charon as one. Their light, their heat, their faint signals blurred together, like two singers sharing the same microphone. Charon's reflection always drowned out Pluto's whisper. It was impossible to know where one world ended and the other began. But in May 2023, as Webb's golden mirrors aligned with precision beyond imagination, that silence finally broke. Using its mid-infrared instrument, MIRI, Webb measured their emissions separately, pixel by pixel, wavelength by wavelength, until two distinct voices emerged from the darkness. One belonged to Charon, colder, flatter, a moon coated in ice. The other was unmistakably Pluto's, a softer, more complex tone, layered with the faint shimmer of its atmosphere. And buried in that light was something extraordinary. When scientists analyzed Pluto's infrared fingerprint, they found thermal emissions coming directly from its upper haze layer. This wasn't random noise or reflected sunlight. It was genuine heat radiating out into space. It proved, beyond any doubt, that Pluto's haze was alive with energy, absorbing sunlight and re-emitting it as infrared radiation. It was cooling itself down, keeping the planet's fragile atmosphere stable in the freezing void. The discovery was so precise, so clear, that even skeptics had to stop and stare. Xizang's bold idea, once seen as theoretical, was now backed by direct observation from the most powerful telescope ever built. Pluto wasn't just an icy relic from the Kuiper Belt. It was a world with an active climate system, one driven not by gases or storms, but by microscopic haze particles that behaved like an invisible thermostat. As the data came in, scientists began to realize the scale of what Webb had done. It hadn't just observed Pluto. It had given it a voice, a chance to speak for itself for the first time since its discovery in 1930. A voice that said, "I am not dead. I am not silent. I am alive with chemistry, light, and motion." From 5 billion kilometers away, Pluto had finally stepped out of Charon's shadow. And what it had to say would change not only how we see this distant world, but how we understand every hazy planet and moon across the cosmos. When the data came through, scientists could hardly believe what they were seeing. For years, the idea had hovered on the edge of possibility, a whisper in the void, a theory too bold to prove. But now, there it was, written in the cold light of infrared. Truth. Pluto's haze was glowing. Webb's instruments revealed faint but undeniable mid-infrared radiation streaming from the upper layers of Pluto's atmosphere, a signal no telescope had ever detected before. It wasn't sunlight reflected off ice, and it wasn't heat leaking from the planet's frozen surface. This was something else, something alive in the physics of it. Those tiny Tholins, the microscopic particles formed when ultraviolet light tears apart methane, were doing the impossible. They weren't just floating passively through Pluto's sky, they were working. Each particle absorbed sunlight, warmed ever so slightly, and then re-radiated that energy back into space as mid-infrared heat. And in doing so, they acted as a planetary coolant, keeping Pluto's fragile atmosphere far colder than it should be. It was as if Pluto's own sky had built a thermal shield, a haze that both protected and regulated it, maintaining a balance in a world where sunlight is 1,000 times weaker than on Earth. For planetary scientists, this was a revelation. Until this moment, they believed that gases like carbon dioxide, nitrogen, or methane controlled a planet's temperature, not solid particles. But Pluto had rewritten that rule. Its atmosphere wasn't cooled by its gases at all, but by a layer of organic dust that behaved like an invisible radiator. This discovery didn't just explain Pluto, it shook the foundations of planetary climate science itself. If Haze could cool a planet here, 5 billion kilometers from the Sun, what did that mean for other worlds? What about Titan, Saturn's moon with its orange haze-filled sky? Or Triton, Neptune's icy twin of Pluto? Or even exoplanets far beyond our solar system, cloaked in dense atmospheres rich with particles and organic chemistry? For the first time, scientists realized that haze wasn't just decoration. It could be the architect of a planet's climate. A single change in the density or color of those particles could shift a world's entire temperature balance. The implications went even further. On early Earth, billions of years ago, our planet's skies may have been filled with similar Tholin, complex organic molecules forming under a young, harsh sun. Could haze have once cooled Earth too, setting the stage for the first stable oceans and eventually life itself? Suddenly, what started as a mystery about a frozen dwarf planet became a question about the origins of habitability. Across the universe, and at the heart of that revelation, stood one telescope, a machine 1,000,000 miles from home, quietly listening to the thermal heartbeat of worlds beyond reach. Pluto had spoken, and the James Webb Space Telescope had heard it, not as a frozen rock, but as a world alive with chemistry, balance, and secrets yet to come. Pluto isn't just an isolated world floating in the darkness of the Kuiper Belt. It's a communicator, a sculptor subtly shaping its companion, Charon. From millions of kilometers away, James Webb's observations revealed something extraordinary. Pluto is slowly leaking methane into space. Not violently, not in a storm of ice, but gently. A faint exhalation of gas escaping its thin, nitrogen-rich atmosphere. Some of this methane drifts across the void, reaching Charon, its large, icy moon. Charon's surface, bathed in this ghostly snowfall of methane, is transformed over time. When sunlight strikes these molecules, and when cosmic radiation interacts with them, a chemical alchemy begins. Hydrocarbons rearrange, combine, and eventually form complex reddish compounds. The result? Charon's iconic red polar caps, mysterious for decades, hinted at in New Horizons images, now explained in vivid infrared detail by Webb. Imagine the slow, silent artistry of this process. Pluto, billions of kilometers from the Sun, breathing out methane, whispering across space. Charon, patiently receiving it, its icy poles slowly painted in warm shades of crimson by chemistry and light. It's a cosmic dialogue, two worlds intertwined, one shaping the other, their fates linked in ways invisible to the naked eye. This discovery underscores a bigger truth. Even the smallest, coldest worlds can have dynamic, interconnected systems. Pluto isn't just a frozen dwarf. It's an active, influential presence in its corner of the solar system. Its atmosphere, its haze, even its escaping gases, all are part of a delicate balance, creating phenomena that stretch across space to another world. And the story doesn't stop there. If Pluto can sculpt Charon from millions of kilometers away, what might other distant, icy worlds be doing? Moons orbiting Neptune, distant Kuiper Belt objects, even exoplanets circling far-off stars. Could they be linked in similar, hidden ways? For the first time, JWST has not only revealed Pluto's internal secrets, but also its cosmic influence, proving that even at the edge of our solar system, planets can interact, shape, and communicate. The red caps of Charon are more than color. They are a signature of interplanetary chemistry, written in methane, sunlight, and time. Pluto speaks, Charon listens. And thanks to the James Webb Space Telescope, humanity is finally hearing the conversation that's been going on for billions of years. Pluto has done something remarkable. It has upended what scientists thought they knew about planetary atmospheres. For decades, we assumed that gases were the primary drivers of a planet's climate, carbon dioxide trapping heat on Earth, methane shaping Titan, nitrogen and methane controlling Titan and Triton, solid particles, haze, or dust. They were considered background players, minor contributors at best. But Pluto shows us a new truth. Haze can dominate the climate. Those tiny tholins drifting through the upper atmosphere aren't decoration. They're powerful regulators, absorbing sunlight and radiating heat into space, cooling an entire world. In a solar system where sunlight is already scarce, this is revolutionary, and the implications stretch far beyond Pluto. Saturn's moon Titan, with its dense orange haze, may be experiencing similar processes. Neptune's moon Triton, icy and distant, could also have its climate sculpted by haze. Even exoplanets orbiting far from their stars, worlds we've barely glimpsed, may not follow traditional gas-based models. If haze dominates, then our predictions about their temperatures, stability, and habitability could be completely off. The James Webb Space Telescope has shown us that what we assumed about atmospheres might be wrong. Planets can have climates driven not by gases, but by the chemistry of particles suspended in their skies. It's a paradigm shift, forcing scientists to reconsider not only distant worlds, but also our own planet's deep past. Billions of years ago, early Earth may have had a haze-rich atmosphere composed of nitrogen and hydrocarbons, much like Pluto today. This haze could have helped regulate temperatures, moderated the planet's climate, and even enabled the chemistry necessary for life to emerge. In other words, Pluto's frozen, distant haze may hold clues to how life became possible on Earth. From a small dwarf planet at the edge of the solar system, we've learned lessons that span planets, moons, exoplanets, and the origins of life itself. Haze, once dismissed as a cosmetic feature, now takes center stage as a cosmic climate engineer, shaping worlds in ways we never imagined. Pluto, Charon, Titan, Triton, distant exoplanets, and even early Earth, all connected by a subtle, invisible force, proving that sometimes the smallest particles hold the biggest secrets. The universe is stranger, more intricate and more alive than we ever thought. And thanks to James Webb, we're finally beginning to see it clearly.